Hello friends, the next topic in MOS capacitor which is to be discussed is the charge distribution, the electric field and electric potential in MOS capacitor with P substrate. So here we will consider a MOS capacitor which is working in inversion mode. Please try to recall what is the meaning of inversion mode. This is a MOS capacitor with P type of substrate, that is P type semiconductor, on which we have the oxide, and then this is the metal gate. So for operation in inversion mode, I apply positive potential to the gate terminal and negative potential to the P substrate. So positive terminal of the battery is connected to the gate and negative terminal is connected to the P substrate. So when you connect positive terminal to the gate, so the gate terminal will acquire positive charges here, maybe like this, and that should have enough strength. That potential should be large enough for the operation of the device in inversion mode. What is the meaning of the operation of device in inversion mode? Please try to recall the energy band diagram. When the intrinsic Fermi level falls below the actual Fermi level at the boundary of the interface, the mode of inversion is called, the mode of operation is called inversion mode. I repeat, when the intrinsic Fermi level falls below the actual Fermi level at the boundary, that mode of operation is called inversion mode. In inversion mode, the conduction band lies closer to the Fermi level, and where conduction band lies, this is the conduction band at interface. When conduction band lies closer to the Fermi level, the device operates, or this layer operates like N-type semiconductor, even though this side, the complete semiconductor, is P-type. So there is inversion of the type of material from P-type to N-type at the boundary. That is why we call it as inversion mode. This is just a revision of what you have studied. Fine. So in inversion mode of operation, there are electrons gathered at the interface between oxide and semiconductor. In addition to that, there is formation of the depletion layer near this region, in this region below the oxide layer. In the depletion region of P substrate, what do we have? We have the uncovered bound charges of impurity atoms. In P-type substrate, what are the impurity atoms? That is acceptor impurity. And acceptor impurity acquires negative charge, so therefore we have negative bound charges of the acceptor impurity. These are the negative bound charges of acceptor impurity. And in inversion mode, there are electrons at the interface gathered like this. Region is what? Region, because at the boundary, conduction band is closer to the actual Fermi level. So this area, this region is behaving like N-type material, where concentration of electrons is more than the concentration of holes. And in fact, when this fall of the intrinsic level is exactly double of this twice of 2q phi f, then it is nothing but strong inversion mode. We have seen that, and again I will discuss it. This is what you have. So let us see the charge distribution. I have positive charge on the gate side. So if you see, this is the energy band diagram. On left hand side of the boundary, I have metal. On this region, I have oxide, and on this side, I have the semiconductor. That stands for MOS. Fine. So at the boundary between metal and oxide, there are the charges gathered on the gate. So this side, I have the positive charge on the metal side. Why? Because it is positive charge. In the oxide, remember, I am assuming here there are no charges stored in the oxide, because oxide is an insulator, and insulator is always free of, it does not have the free charges. All charges are bound charges. Fine. So I am assuming there is no charge inside the oxide, but this is not a fact. We will see it at later stage. Here I am assuming there are no charges stored in the oxide layer. So there are no charges inside the oxide layer. Now come at the boundary, that is interface. At the interface, the type material is behaving like N-type. So there is large negative charge at the interface and at the boundary. And this charge exists only in the narrow region near the interface. So this exists only for the narrow region. What is the if W is the total width of the depletion layer? Why depletion layer? Because when we apply positive charge, so the holes from this region are moved out. So this is the W. If you talk about this is the width of the depletion layer here. Fine. So here it is W. So in depletion layer, what I have the negative, that is electrons, free electrons at the interface, because of which I have spike in the negative charge. Then I have the negative bound charges in the depletion region. QD stands for the charge in depletion region. Fine. So on the semiconductor side, I don't have a uniform distribution. Rather, at the boundary, I have the peak negative charges because of electrons. Then I have the bound charges of acceptor atoms. On the left hand side, I have the positive charges on the metal plate. So this is the charge distribution in the MOS capacitor. Fine. Let us talk about electric field now. In electric field, you can see it is just like a parallel plate capacitor. On one side I have positive charge, on another side I have negative charge. Although on one side it is concentrated, on other side it is distributed. So electric field between the two plates of a parallel plate capacitor is always constant. Remember this. Electric field in a parallel plate capacitor is constant. And if you remember, the electric field in parallel plate capacitor is given by what? The charge density by epsilon. You need to recall your electromagnetics for that purpose. If you have the surface charge density and divide it by the permittivity of the medium, I get the electric field intensity. So electric field intensity here is constant. This combination is behaving like a parallel plate capacitor. In parallel plate capacitor, charges are concentrated on one plate and another plate. Here charges are concentrated on metal, but it is distributed on the semiconductor side. Distributed over which region? Distributed over the depletion region. Fine. But remember, just like parallel plate capacitor, the electric field is constant here, that is in the dielectric, and it falls suddenly and then decreases linearly in the depletion region. The electric field in the depletion region we have already derived in p-n junction. So just remember that in dielectric it is constant and it reduces linearly in depletion region. Fine. Now, if you talk about the potential, we will see, just visualize this circuit. Total voltage is V. That voltage will be dropping across this. So some part of this voltage drop across the oxide layer. Second part of this voltage drop across the depletion layer. So one part of the voltage which drop across the oxide layer is VOX, that is voltage across oxide layer. The remaining part, it drops across the depletion region, so that is phi s. Why phi s? Because phi s is surface potential, which is nothing but potential across the depletion layer on the MOS capacitor. I have already discussed in my previous video. So this is what you need to remember. Now let us go for some mathematical analysis. Here, if you see what is the total charge QD in the depletion layer. The charge in the depletion layer, and remember it is not charge, please let me correct. Q is not charge. In this case, Q is the charge density, that is what charge per unit area. I will be taking Q, not the charge, capital Q, it's rather capital Q, not small q. In my EDC notes, in EDC lectures, small q I have taken for charge of electron or hole. But here I am using this symbol Q. Q is not charge, rather it is charge per unit area, that is the surface charge density. So here, if you take the charge per unit area on the metal side, that is nothing but Qm. Come to this side, that is on depletion region side. So let us find the charge per unit area of the depletion region. The charge per unit area of depletion region is given by Q, that is charge of each electron, or charge of each what? Charge of each acceptor atom, that is negative charge, that is equal to 1 electron, multiplied by the acceptor impurity, right, multiplied by width of the depletion layer. If you talk about the volume, so volume, this is the charge per unit volume, multiply it by that, you will get the charge per unit area of the cross section of the capacitor. This is negative here, right? What is maximum charge? Maximum charge density, you can say, this is charge density, not charge, this is nothing but charge density in what? In depletion region, that is in depletion region, right? So here, what is the maximum charge density? QD will be maximum when it is Q and A, when W is maximum, when W is maximum. And if you remember, what is maximum value of W? The maximum value of the depletion layer width in my previous video, if you have seen it seriously, the expression of W max is nothing but under root 2 epsilon by Q into 1 by NA into the surface potential, and that surface potential is for strong inversion for maximum value of P, and for strong inversion this is nothing but 2 phi F. I will rewrite it like that is 4 epsilon, and this is what? Permittivity of the semiconductor. I will take 4 epsilon S by Q into 1 by NA, and what is phi F for acceptor type of, that is P substrate, that is nothing but KT by Q in ln NA upon NI. This is what you need to remember. This is the maximum width of the depletion layer, and if you put this here, you get the maximum charge in the depletion region. Fine, that's the charge distribution for depletion region. I cannot calculate Q directly, but I have given you the expression of the charge density in the inversion layer. You can see previous videos. I have also given you the expression of the charge density on the surface, that is interface. You can see the previous videos for that purpose. But here, what is the total charge on the material? The total charge on metal plate or metal gate, you can say, total charge is nothing but Qm, and if I say total charge on the semiconductor side, so is equal to minus Qs, that is Qs is what? Qs is total charge on the semiconductor side, right? So I will assume let Qm is the charge, Qm is the charge at the interface, that is minus Qn, not Qm. So this is equal to minus Qd minus Qn inside the bracket, or you can put it here, that gives what? That is equal to minus Qd was what? Qna into W minus Qn, negative sign here, and that gives the total positive charge is equal to Qna W minus Qn, not minus, plus Qn. This is the total positive charge. Why so? Because the capacitor is always electrically neutral. The positive charge on the metal gate must be equal to the total negative charge in this region, that is on the semiconductor side. So that is why I have taken total charge on the metal plate is equal to negative of the total charge in the semiconductor, or we can say charge density on the metal side must be equal to the total charge density on the semiconductor side, assuming this area of cross section is same. Fine. So now there is one interesting relationship. I have got Qm, and if I want to find the voltage drop across the dielectric layer, voltage drop across layer. What is this dielectric layer, or you can say oxide layer? I'm sorry, oxide is basically dielectric material, so that's why I have written dielectric, because of just nature of the material. Now, what is voltage? Voltage across the dielectric material is equal to nothing but Qm by what? The capacitance of dielectric. Q is equal to what? CV in case of a capacitor. So total, or you can say, I'll write it like this: the total charge on the each plate of the capacitor is related to what? That is Qm is equal to COX. COX stands for capacitance of this what? Oxide layer into, that is, voltage drop across the oxide layer. That is the relationship. And for oxide layer, you should remember the expression of the capacitance. For oxide layer, remember the capacitance COX is given by epsilon OX by TOX, where what is epsilon OX? Epsilon OX is the permittivity of the oxide layer. TOX stands for thickness of oxide layer. That is the thickness of oxide layer. So this gives the capacitance of oxide layer. Please do remember this. This is very important. And this is very important. Remember these expressions. I will be referring in future. In future means in my further next videos. Fine. So here I can replace Q by minus QS. So this gives Q minus of QS is equal to what? That epsilon OX by TOX into VOX. That's what you have. Or I can rewrite the voltage drop across oxide is equal to, that is, minus QS by epsilon OX into TOX. So if you have to find the voltage drop across the oxide layer, that is equal to minus QS stands for negative of the, that is basically the total negative charge on the semiconductor. That is equal to total positive charge on the metal. Fine. And I have given you the expression here. So this is what you have. But what is the total potential here? Please see this total potential. So total potential or total voltage across capacitor is what? That is equal to what? From here to here, that is V. From this gate terminal to the terminal of substrate, so that is capital V. So capital V is equal to drop across this layer plus drop across the depletion layer. So voltage drop across the oxide layer plus voltage drop or potential drop across the depletion layer, and potential drop across the depletion layer in MOS capacitor is what? That is called surface potential. That is represented by this. This is QS, that is energy, but phi S stands for surface potential. So that is phi S. So this is equal to phi S. Fine. This is the expression of the externally applied voltage. Sometimes it is denoted by VG. VG stands for gate voltage. Here, just for this particular case, I am taking it V. So I can rewrite for strong inversion. I have given you the expression for strong inversion. Phi S is what? Twice phi F. So this gives the external applied voltage will be equal to VOX is nothing but minus QS by epsilon naught X into T naught X plus twice phi F. That is the expression of the voltage, external voltage drop across the capacitor in terms of the charge stored in the semiconductor region, then permittivity, sometimes we call it as the dielectric constant, thickness, and phi F. Phi F is what? That is nothing but energy difference between the intrinsic energy level and actual Fermi level. Fine. So this is what the topic is. I have given you the expression of the potential. I have given you the expression of the charge. I have not taken this because you don't have direct questions on electric field, but just for the diagram, there may be one question on diagram. I have given all the diagrams and mathematical relations. Further, I will be talking about the next topic, that is maybe flat band voltage and threshold voltage, which are the important topics. I am discussing everything to make you understand about this MOS capacitors. Till now, whatever I have discussed, there was no direct question in gate, but since these days lot of questions are coming from this topic, you should understand each and every bit of the topic, that is MOS capacitor. And later on, when I switch over to the flat band voltage and thermal voltage and capacitances, there I'll be discussing the numericals which have appeared in gate. Till then, I'm trying to build up your concepts and facts. So just wait for the next video where I'll be talking about the flat band voltage and threshold voltage. Thank you very much for watching the video.